Hi guys, in this video I'm going to talk about photodiode and its working. In fact, to be precise, it is a PN junction photodiode. As it is diode, it's a two-terminal device which responds to photon absorption. That's why it is called a photodiode. Or we can say which converts light to electrical current. So to start with, let me take a normal PN junction diode, its current equation and its IV characteristics as reference. Here I have taken a normal PN junction diode circuit symbol for simplicity, where I have shown the reference current direction of the diode and the reference potential across the diode, VD. And the current equation for the diode is given here, that is ID is equal to I0 times e power VD over VT minus 1. And the characteristics are drawn here. In this characteristics, this value of current that is flowing, we have represented this as I0, which is called the reverse saturation current. And that is this I0 value. Now we want to take this diode, let's say it is operating at a particular voltage, and we want to incident light onto this PN junction diode and see what happens. So as we are assuming there is some potential applied in reverse bias for this diode, so let's see how that energy band diagram would look to start with. Let's say the potential that is applied here is VR, which means VD is equal to minus VR. So in that case, the energy band diagram would look like this, where the entire energy band here would be equal to Q times VBI plus the applied reverse bias voltage. In fact, here the Fermi energy levels have split, and the difference between them would be Q times VR. In fact, in this energy band diagram, if we see, the slope of this energy band diagram is 0 here, which means the electric fields are 0 in these regions. And in this region, the slope is negative, which means the electric field is directed in the negative x direction, assuming this is x direction. So we have electric field in this direction. Let's say that is electric field present here in this depletion region, where we have this energy band bent. Now in this case, when there is no incident light, the current that is flowing is I0. Now let's say we are going to incident light onto this PN junction. Let me assume the light is coming from one side with the energy h nu. Let's assume that this light energy, that is h nu, is enough to actually excite electrons from valence band to conduction band. In this case, let's say electron hole pairs are generated in the depletion region. Let's say there is an electron here that is generated and hole by absorbing this photon. So electron hole pairs are generated. So the first point is carrier generation by incident light. Now as this electron hole pairs are generated, let's say in the depletion region where we have electric field, this electric field would separate this electron hole pairs in, the holes would be sent into p side and electrons would be sent to n side. This is p side, this is n side. So the second point is carrier transport or in some cases and carrier multiplication, especially when we talk about the avalanche breakdown region where we have carrier multiplication. Let's not get into that detail at this point. This incident photon has created electron hole pairs in the depletion region where electric field is present, which separates the electron hole pairs, which is this second point. The carrier transport is taken care because of the existing electric field in the depletion region. If suppose this photon creates electron hole pairs in the neutral regions, let's say n and p, in which case the electrons holes anyway have lifetime and there is no separation between them because there is no electric field here, so they would recombine back again. There wouldn't be carrier transportation happening, which is the second point, in neutral regions if there is excitation and creation of electron hole pairs. So that's a point why we are discussing only about the depletion region here. That's what actually matters. Now if we compare, when there was no incident light on the PN junction, the amount of current that was flowing was I0. So if you look at here, by having incident light, we created more carriers. Hence, the amount of carriers present for conduction are more. As a result, the amount of current that flows in reverse bias because of the incident light would be more, which means the amount of current that we would see would be higher now at this given voltage. The amount of current that flows in the reverse bias is not really dependent on the potential that we apply, because the availability of the carriers play a major role than the potential that we apply. Hence, the current is constant. So taking that, the current is going to be constant. But the question now is that what will happen to the current when we have the voltage across the diode 0? So which means when Vd is 0, this is the line that we have, where would this current actually hit? Would it become 0 or would it be non-zero value? Just pause the video and think about it. When Vd is 0, let me take the energy band diagram and show the circuit symbol with the connection. This is under equilibrium or short-circuited case, where we have this barrier which is Q times Vpi because of the built-in potential. Of course, there is no external applied potential, and we would still have the equilibrium depletion width. Obviously, as we have the slope, we still have electric field present in the depletion region, and of course it will be less than what we have in the reverse bias case. Now, if we actually have incident light here, it would still create the electron hole pairs, and the electric field would separate them still, where electrons are sent to n side and holes are sent to p side, which means because of this incident light, the current that is flowing is actually in this direction. If you observe, that is, holes are sent to p side, which means the current because of holes is in this direction. Electrons are sent this side, which means the current is in this direction. So the entire current because of the incident light is n side to p side. So which means when we look at this, the current that actually flows will be in this direction because of the incident light. So let me represent here that there is incident light. So that's why ID is not going to be 0 when the potential applied across the diode is 0, which means in this case Vd is 0. And yet ID is not 0. But ID in fact is a negative. So which means if you look at this scale, so this is negative side. So the current is going to be negative value because it is flowing in the opposite direction to that of our reference direction. Now the similar kind of circuit, let's see in this case that when we had reverse bias applied, Vd will be negative. With respect to our reference, the potential applied is minus. So Vd is equal to minus Vr. And in fact, the current that was flowing, in fact in reverse bias, the current that is flowing is I0 this way. So hence ID is equal to minus I0. But of course, because of the incident light, there is extra current that is flowing. So that extra current is also in this direction. So that we would call current due to incident light. Hence we would say that is IL. So which means this is minus IL. So that's what we have shown here. So in this case, we have this IL flowing. In equilibrium, this current would have been 0. But because of the incident light, let me show that also here, that this is not a diode with no incident of light. Here we have light incident, due to which there are electron hole pairs created in the depletion region, which are separated due to the electric field in the depletion region. As they are separated, when they reach to the terminals, they will be collected outside. Hence, you would see a current flow which is extra compared to a diode which is not exposed to light. Now, the question is, we have seen when it is reverse bias, we have seen when Vd is 0. Now, what will happen when we forward bias this? The question is, when we forward bias, the current would be positive if there is no incident light. Even when Vd is positive, the electric field still will be directed inside the PN junction from N side to P side. Because we know on N side we have positive ions and on P side we have negative ions. Electric field is always directed from N side to P side inside. Which means even if it is in forward bias, the incident radiation, if it creates electron hole pairs, current, because of the incident light, is still going to flow from N side to P side, which will be in fact in opposite direction to that of the current that is flowing in the forward bias of a diode which was not incident to light. So if you observe these characteristics, the current is almost zero in this case in forward bias. So the current that will be present will be still this IL. So the current that will still be there will be IL. But as we increase the forward bias, there would be a forward bias current which will be acting in the opposite direction to that of the IL. Hence, the current would keep decreasing in magnitude. And eventually, it will meet this curve. This is, let's say, for a incident radiation intensity 1. Now, let's say we increase the intensity. What happens? When we increase the intensity, which means the number of photons coming per unit time would be higher, which means the number of electron hole pairs generated would be higher, which means the number of carriers collected at the two terminals would be higher, which means the current would be higher. So I can draw another curve showing as intensity increases, the current would increase. I have shown the IV curve here where intensity is increased. So we know when there is no incident light, there is some current flowing. We call this current as dark current, which makes sense because there is no light present. Let me take this IV characteristics in a different paper and let's understand that in detail. What is this point called? What is this point called? And what are these regions? I have taken the IV characteristics of a diode without any incident light, and I have taken with some light intensity onto the PN junction where the IV characteristics are like this. Now in this case, let's investigate the current times voltage. In the first quadrant, current is positive, voltage is positive, hence V times I is positive. And we don't have any business in the second quadrant because there is no current, no voltage here in the quadrant. Coming to the third quadrant, the voltage is negative and current is negative. So V times I still is positive because negative times negative is positive. But when we come to the fourth quadrant, V times I, if you observe that V is positive but the current is negative, which means V times I is negative. This is a very important point, and let's see why this is so important. If you recollect the network theory concepts where we have a resistor, for example, when current is flowing through it, we have positive potential here and negative potential here, which means current enters through higher potential point. Whereas when we take a voltage source, for example, we have positive this side, negative this side. Current in fact leaves the positive potential side. You see, it is opposite in fact. So in resistor case, the current is entering through the higher potential point where V times I is in fact positive, and when current is leaving from the positive terminal and entering into the negative terminal where V times I is taken negative. So it means the supplier's power is negative and the absorber's power is positive. Hence, usually in network theory, we say the entire power in a circuit is zero because there are sources whose power is negative and there are guys who are absorbing the power whose power is positive. So if you observe in this fourth quadrant, we have that V times I is negative, which means we are actually going to supply power. So what we have done here is we have converted the photon energy or light energy into electrical energy. If you operate the photodiode in this region, it's going to actually supply power. So if we operate photodiode in this region, we can actually find out the presence of light and its intensity, which means we can detect signals. So for optical communications, we can use photodiode in this region to detect light signals. So we can say in this region it is behaving like a photodetector. So in fact, in the next videos, we will do a video on a PN junction as a solar cell or photovoltaic cell or PV cell, And in another video, we will investigate on a photodiode acting as a photodetector in detail. So before we move on to the next video, let's investigate these 2 points, which are very interesting. This point is, when the potential applied across the diode is 0, we have some current. So we call this current as ISC, which is short circuit current. And when the current is 0, we have a potential, which we will call this as open circuit voltage. So coming to VOC, where the diode is actually open circuited, but there is incident light, in which case our reference was actually positive, negative, this is VD. We are going to measure some potential here, not 0. So even when it is open, when light is incident, we will measure potential. So let me put this here, intensity equal to 0, then we will see VD is equal to 0. But if intensity is not equal to 0, we will see VD positive, not 0. So that's what I'm calling here. That voltage that we measure across this diode when light is incident is called VOC. That's the open circuit voltage. And now coming to ISC, which is short circuit current. So we have diode and we short the terminals, and ideally in a normal diode where the intensity of the light is, let's say, 0, which means there is no light incident, the current that would be flowing through the diode would be 0. But whereas when intensity is not equal to 0, when there is incident light, there would be current flow. In fact, that current flow would be in the opposite direction to that of our reference. Our reference is ID, which is from P side to N side, but the actual current, which is IL, that's going to flow from N side to P side. That current we are going to call as ISC, which in fact would be equal to a negative value. So these two are very important points. When we go to photovoltaic cell or solar cell, we would be using these terms very often.